Welcome to the lecture 36. So, in this lecture I am going to discuss about comparison between vector spaces and free modules over arbitrary rings. So, let me start vector spaces over fields versus free module over arbitrary rings. So, we know that every vector space has a basis, okay, but this is not true in case of modules. We have already seen several examples. If a module have a basis, then we call it as a free module. So, but vector spaces has very nice properties which may not true for free modules, those we are going to discuss now. So, for vector spaces over fields, and we are looking free modules over arbitrary rings and also free modules over commutative rings, okay, with unity. So, the first property I am going to discuss is every linearly independent set can be extend to a basis, okay, this we know already for vector spaces, but whether it is true for the, for example, if you look at free modules over arbitrary rings, so we will see that this is false, okay. So, we will see with an example 1, I am denoting as E1. Similarly, free modules over commutative rings, whether if you take any linearly independent set in a free module can be extend to a basis of that free module, it is even not true for free modules over commutative rings. This also false, we will see example E1, okay. So, second one, every spanning set of a vector space, spanning set another name is generating set, okay. I am just generating set. Every spanning set contains a basis, okay. This is, we know that true for vector spaces, but it is also false in case of free modules over arbitrary rings. So, I will give an example E2. Of course, this is also false in case of free modules over commutative rings. The next property is every subspace of a vector space, is a vector space, okay. But in case of free modules this is not true. If you replace subspace with submodule and vector space with left module, then this statement is still not true, it is also false. We will see an example, let us say example E3, this is also false, we will see example E3. The same example will work. If we give example for commutative rings, then it is also works for arbitrary rings as well. Next property is any subspace of a finite dimensional or finitely generated or finite dimensional, any subspace of a finitely generated vector space is finitely generated, okay. So, it is still finitely generated, means the subspace of a finite dimensional vector space is finite dimensional, but this is again false. We will see the same example, one example E3, this is also false over commutative rings. So, it is, this property is again failing in case of modules, free modules over commutative rings. And final, any two bases of a vector space have the same cardinality. Okay. So, any two bases of a vector space have the same cardinality, but even this is also false in case of free modules over arbitrary rings. Okay, we will see an example E4. And in case of, surprisingly, this is true in case of free modules over commutative rings. Okay. So, I will give the proof in this case. Okay. So, now let me give the examples E1, E2, E3 and E4. Okay. So, now I am going to discuss about these examples. So, example, okay, E1. Okay. So, what is this example? Any linearly independent set in a free module need not contain a basis. Okay. So, for this one, so let us look at R, ring R as the ring of integers. So, M is Z itself. Okay. So, we know that it is M is a free left R module. It is a free left R module. What is the basis? With the basis, one basis I can give, that is singleton 1. Okay. Our ring R is Z, Z contains unity, it is a commutative ring. So, therefore, M is a left R module, it is a free left R module with basis singleton 1. But if you look at, take it as S, so this is singleton 2, okay, the integer 2. So, then this is contained in M. Okay. Note that S is linearly independent, right. So, singleton set 2 is linearly independent. If I take any Z combination of 2 is 0 means that integer has to be 0. So, but S does not contain a basis of M over the ring R, which is Z. Okay. So, suppose if it contains, let us show this. Suppose this S contains, sorry, here let have one correction, but S cannot extend to a basis of M. So, let us prove this. Suppose there exists a set, suppose there exists a basis, let us say B, there exists a basis containing 2, say that basis, say that as B. Okay. So, then if B is equal to singleton set 2, then B does not generate M over Z. M is Z itself. Okay. So, why? Because 1 we cannot return as 1 belongs to M, but because 1 belongs to M and 1 cannot be a Z multiple of 2. Okay, 1 cannot be a Z multiple of 2. So, therefore, B cannot be a generating set. But whereas, okay, so if B contains an element, say B belongs to B and B does not equal to 2. So, then we have, then if you look at 2 comma B, this is contained in B is linearly dependent. Why? Because of this relation 2 times B minus B times 2, this is 0. This is our non-trivial linear combination equal to 0. So, why? Because this B belongs to B and this 2 is also belongs to B. So, therefore, if we write like this and Z is a commutative ring. So, therefore, if we are writing, so we will get a non-trivial combination which forces that B is 2 comma B is linearly dependent. This implies that, so this implies that B is linearly dependent. Thus, we have a contradiction, right? Why? Because we started with B is a basis. So, that means that B should generate M, and not only that, B is linearly independent. Okay. So, therefore, we have this contradiction. Therefore, singleton 2 is a linearly independent subset, but this we cannot extend to a basis of Z over Z as a left module. So, now let us come to the next example. Okay. So, let us say E2. So, what is this example? So, this example is corresponding, there exists a spanning set or generating set, both use, there exists a spanning set does not contain a basis. Okay. So, this is for we are doing for the free modules. So, for that one, let us take it as R is Z, the ring of integers, and M is again Z. Okay. So, then this is a left free module over Z. Okay. But we know what is the basis. With the basis is singleton set 1. Okay. So, with basis singleton 1. So, now let me take two integers m and n belongs to, okay, positive integers, of course, it is contained in Z, positive integers, such that GCD of m and n equal to 1 and m and n, these are non-units, okay, non-units in Z. That means that m and n are not equal to 1. Of course, they are positive integers, they know they are not equal to minus 1. So, then GCD of m and n is this one. So, now let me take x equal to m comma n. Okay. So, this is a subset of m. Okay. So, since its GCD is 1, there exist two integers, let us say a b belongs to Z, such that 1 we can written as, such that 1 is equal to a m plus b times n. Okay. 1 equal to a m plus b n, because the GCD is 1. So, that means if I take x, so this is equal to a x m plus b x n for any x belongs to Z. Okay. Our Z is m. Okay. So, that means that we can written as Z is equal to mz plus nz. Okay. So, Z equal to mz plus nz. So, that means that therefore, x, if we take m comma n, so then this is, of course this is our m. This is a generating set, say generating set of m over the ring R, which is equal to Z. Okay. M comma n is, this is a generating set, but m comma n, but x is not a basis. Okay, it is a generating set of m over Z, but x is not linearly independent. Okay, why? Because since m into n minus n into m, this is 0. Okay, so this belongs to x, this belongs to x. So therefore I have this some kind of a trivial expression. So this forces that x is not linearly independent, and hence x is not a basis. X is not a basis of m over Z. Even and also mz is not equal to Z, okay, and nz is not equal to Z. Why? Because since m and n are not equal to 1, because they are non-units. So once they are non-units, the ideal generated by m is not equal to Z, the ideal generated by n is also not equal to Z. So therefore that means, this means that singleton set m and singleton set n, this cannot generate m. M means Z, okay, over the ring Z. Okay, these are, therefore this does not generate Z. That means that x does not contain a basis. Okay, does not contain a basis of m over Z. Okay, so that means that if you take any spanning set, but X is a spanning set, therefore the spanning set does not contain a basis. Okay, so but whereas this is true in case of vector spaces. Now let us come to next example. So example E3. So what is this example? Submodule of a finitely generated, okay, finitely generated submodule of a finitely generated free left module need not be finitely generated and need not be free. Okay, it need not be finitely generated as well as it need not be free. So now let us look at example. Yeah, so let me take the following, let K be a field, and let me take, let R is equal to K of x1, x2 and so on. I have infinitely many variables, polynomial ring in infinitely many variables. So let m is equal to R itself, okay, m is equal to R itself. So then we know as usual m is a free left R module and finitely generated also, right, because our base is contains singleton set 1, therefore singleton set 1 is a finite set, this generates m over r, therefore it is finitely generated. It is a free left R module and it is also finitely generated. Now let us consider n. So now what are the submodules of M? Those are precisely ideals. It is a commutative ring because it is a polynomial ring, therefore it is a commutative ring. So consider n equal to the ideal generated by all the variables x1, x2, x3 and so on. Okay, n, this is contained in M, of course M is nothing but R. So submodule means the ideal generated by, means it is a commutative ring, left ideal, right ideal or two sided all are coincide. The ideal generated by the variables x1, x2 and so on. Okay. So now the first claim is n is not finitely generated. Okay. So n is not finitely generated. So let us try to prove this. Now the claim, let me write it as a claim. So now proof, suppose it is finitely generated. Okay. Suppose n is finitely generated as a left R module or a left R module, say generated by, so generated by the polynomials f1, f2 and so on comma some fr. Okay. So these are all belongs to n. Left R module generated by f1, f2 and so on comma fr. So then there exists some natural number n such that, so all these fi's f1, f2 and so on fr, so all these belongs to just simply polynomial ring in this n number of variables. Okay. So precisely the variables which are present in the monomials corresponding to the polynomials f1, f2, fr. Okay. So that means that n is, so f1, f2 all these belongs to this, and of course this is contained in the ring R. And also all these fi's have no constant term. Why? Because all fi's belongs to n. It is generated by the variables. So n is nothing but the generated by the variables x1, x2 and so on. So therefore if there is a constant term, then it cannot belongs to n. Okay. So therefore it is all n belongs to this one. So now we have, if you look at xn plus 1 variable, okay, so this belongs to n, but we assume that n is generated by f1, f2, fr. So that means that x n plus 1 we can written as some combination of, let us say a1 f1 plus a2 f2 plus and so on plus ar fr for some, okay, for some ai's, for some ai's belongs to in the polynomial ring, okay, for some ai's belongs to R. Okay. So now let us take x1 equal to x2 and so on equal to xn, take it all these equal to 0. So f1, f2, fr these belongs to, if you look at this one, these are all polynomials in n variables only. Okay. So therefore, if I substitute x1 x2 xn equal to 0, then what can you say about f1 of 0 0 and so on 0, this is 0 and so on, f4 of 0 0 and so on 0, this is also 0, because there is no constant term. Therefore, we will get x n plus 1, this is equal to, take n plus 1 in the above expression, so therefore, x n plus 1, this is equal to 0 we will get. So, but which is absurd, okay, because x n plus 1 is a variable, it is a free variable, it is equal to 0, this is absurd. So, therefore, n is not finitely generated, okay, n is not finitely generated, even n is not a free R module. Why? Because n is not finitely generated, therefore, it is n is also not a free module, thus n is sitting inside M, but M is equal to R. This M is, it is a finitely generated, so n is contained in this is a submodule, this is finitely generated and free also over Z over R, but if you look at n, this is not finitely generated and it is also not free over R, okay. So, this will provide example to the part 3 and 4 what we have discussed.